Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. So in today's topic we'll see the some critical thinking problems in the module 2 actually. So from the tutorial question bank. Now in the module 2, so basically it is focusing on partial differential equations and so basically how do you classify the partial differential equation and based on the physics of the equation, so how do you see whether it is a low speed flow or high speed flow or let's say supersonic or hypersonic flow. So these things are actually basically taught in the PDE equation, and the different physics of the science and technology are explained basically in the second order partial differential equation. So the generalized equation is being taken, and from that generalized equation, so we will actually see so how the physics of the fluid changes, and let's say heat transfer problem or the fluid mechanics or fluid dynamics problem. So how does it see those things are basically discussed in the module 2. So coming to the discussion of the tutorial question bank in the module 2. So I have taken one question. So where classify the following partial differential equations according to the nature as elliptic, parabolic, hyperbolic. So here we have unsteady thermal heat conduction equation we have. So we have Laplace equation we have. So we have second order wave equation. So we need to see so basically what is elliptic, and we need to see what is parabolic, and we need to see what is hyperbolic actually. Okay, so those things we need to see. Then we will see basically A. So A is nothing but unsteady thermal conduction equation actually. So when I say unsteady, so basically you need to have the derivative term dou by dou t. Okay, since we are discussing with the thermal, so the temperature effects are very important. Thermal. So conduction equation. So it can be 1D, it can be 2D, it can be 3D. So if we see 1D, so basically let us take it as alpha into dou square t by dou x square. So this will be the 1D one actually. Okay, one dimensional. So if you see it as 2D, so same dou t by dou t is equal to alpha into so dou square t by dou x square plus dou square t by dou y square. So this is coming to be 2D. Okay. So when I say it is 3D, so dou t by dou t is equal to alpha into so dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square. So this is basically a 3D. So when you see the equations, let us take this as 1, this as 2, this one as 3. So in the equation 1, you have dou t by dou t term. So capital T is nothing but the temperature, small t is nothing but time. Okay. So this first term is contributing for the unsteady thing actually. Okay. The first term which we are discussing, so basically it is contributing for the unsteady. So when I say thermal conduction, so the RHS you can see. So when you have dou square t by dou x square. So let us take a 1D element. So let us take a rod. So where length is greater than the diameter of the rod. So then we can say this element as 1D. Okay. So when the length is very greater than diameter of the element, so we can say it as 1D element. So for the 1D element, so here when we say unsteady thermal heat conduction, so let us say they have end A, we have end B. So at end A, the temperature T is equal to TA is equal to, let's say it is 350 Kelvin actually. So at B, it is like TB is equal to 280 Kelvin. So here we are applying heat actually. So let's say at this end we are applying heat. So how does the heat transfer will take place from this region to this region, this region, this region, this region, this region, every region. So this is what we need to investigate using this 1D heat conduction equation. So here, the conduction phenomena will take place because of the collision of solid molecules, so which is present inside this rod. So here, when you increase the temperature, so the molecules will have the random motion and they begin to vibrate. So because of this temperature, so they begin to oscillate about its position. They collide with each other. With that, the internal energy will increase, so that the temperature from one region to other region will keep on increase. Let's say the temperature has increased at this region, so after a certain time it will increase at this region, so at this region, so because of the collision between the molecules. So therefore, because of the collision between the molecules, so the temperature rise is happening, so this form is called the conduction. Okay, so we have 1D heat conduction equation, so we have 2D heat conduction equation, and we have 3D heat conduction equation. So this is coming under unstudied thermal conduction equation. Okay, so next we have the Laplace equation, so which we will discuss. Now, coming to the classify the following partial differential equations. So we have A, B, C. So based on the elliptic, parabolic, and hyperbolic, we need to see first. How do we classify the elliptic equation? How do we classify the parabolic equation? Like how do we classify the hyperbolic equation? So first of all, what is the criteria to have the equation is elliptic, or to have the equation is parabolic, to have the equation is hyperbolic? So here we have 1D unstudied thermal equation, heat conduction equation. So we have 2D. So let's say we have 3D. Okay. So if you take 1D heat thermal heat conduction equation, so we have basically the coefficients of A, coefficients of B, coefficients of C. So let's see here first how do we get those elliptic, parabolic, and hyperbolic. So first, already which we have seen in the previous sessions. So this is the generalized equation, and from this we have the second order partial differential equation. So which is of 2D. So here you can see we have derivative with respect to x, and the third term we have derivative with respect to y. So this is called the mixed derivative. So this equation we have one. Next, so we have the chain rule terms. So when we do the chain rule terms, so we have this equation which is the chain rule term. So this is the second equation. So we have dou square phi by dou x square term, dou square phi dou x dou y term. Okay. Next, similarly, third equation, the mixed derivative term is available, and we have dou square phi by dou y square term. Okay. So what we do is like for the Cramer's rule, so we collect these coefficients, and when you collect these coefficients, equation 1, 2, 3, so we are evaluating. So what is the value of the mixed derivative? So in this way, so when you are evaluating the value of mixed derivative, so what we are doing is, so we have the coefficient matrix. This is A, and this matrix. So in the coefficient matrix, so what we are doing is like, so this second column is replaced by the constant term actually. So we can see H, we can see dou phi x, dou phi y. So here you can see this H as a constant term. So we have H here. So here you can see that d phi of x is a constant term, d phi of y as constant term. So basically that's why you can see in the second column of A matrix we have replaced this. Okay, and so this is the methodology to solve the variables using Cramer's method. So when we do this aspect, so what happened actually? So we need to see what happens when the coefficient of matrix A, the det is becoming singular. Let's say mod of A is equal to 0. Okay. So what are the criteria? So by doing this, we will get an equation in the form of A into dy by dx square plus b into dy by dx plus c is equal to 0. In this form we will be getting. So which is of quadratic form. So when you have this quadratic form, so when you do the discriminant, in order to find the roots, so dy by dx of 1 comma 2, which is equal to minus b plus or minus under root of b square minus 4ac divided by 2a. So this is what we have. Okay. So here we need to see the value of the discriminant. So this one. Okay. So based on this, we will get to know. So if b square minus 4ac is greater than 0, what we have? Equal to 0, what I have? Less than 0, what we have? So we'll see here. Okay. So based on the b square minus 4ac term, so we will classify. So let's say b square minus 4ac less than 0 is elliptic. B square minus 4ac equal to 0 is parabolic, and b square minus 4ac is greater than 0 is hyperbolic. Okay, so here you have some certain example, so which is elliptic equation. So we will discuss for the tutorial one. So first we will see in the tutorial question. So we need to see which we have the conduction equation, we have Laplace equation, and we have second order wave equation. So let us see. So what happens for the conduction equation? So we take 1D. So let us consider it as 1D. So dou t by dou t is equal to alpha into dou square t by dou x square. So we have this. Okay. So dou t by dou t is equal to alpha into dou square t by dou x square. Now, so here if you see what happens actually, so we need to see what is the value of b. So we need to see what is the value of a, and we need to see what is the value of c actually. Okay. So now let us take the generalized equation. A into dou square phi by dou x square plus b into dou square phi by dou x dou y plus c into dou square phi by dou y square is equal to 0. Okay. So let us compare this equation with this equation. So here we can see a as let us take is equal to alpha, and there is no mixed derivative. We take it as b is equal to 0, and so we don't have any derivative of with respect to y. So we take it as c is 0. So let us take what is this? B square minus 4ac value. So what happens? So here the value of b is 0, 0 square minus, so 4 into a is alpha, so c is 0, so therefore this will be 0. So this is coming under parabolic equation. So unsteady thermal conduction equation is coming under parabolic equation. So in the previous sessions we have seen what is the signification of the parabolic equation. So we saw that for the parabolic equation, so we require the initialization. So it is basically the initial value problem. So at time t is equal to 0, so let us take again the 1D element. So this is A and this is B. Okay. So we are applying a temperature T of A, let's say 500 Kelvin here at T is equal to 0 seconds. And at same T is equal to 0 seconds, at this point TB is equal to, let's say, 280 Kelvin. Okay. So that initialization, let's say at T is equal to 0 seconds, let's say at X is equal to 0, so T of A is equal to 500 Kelvin. So this is one initial condition 1. So let's say T is equal to 0 seconds, X is equal to L, so TB is equal to, let's say it is 280 Kelvin. So this is condition 2. So in this way we need to give the initialization. So basically this parabolic equations, so where the discriminant is 0, so D discriminant is 0, so therefore the parabolic equation is basically the initial value problem. So where we have seen unsteady heat conduction equation. Okay, so let us see the Laplace equation actually. The second thing. So Laplace equation, you can take it as dou square u by dou x square plus dou square u by dou y square is equal to 0. So this is coming from the diffusion term, the momentum equation, or else you can see dou square t by dou x square plus dou square t by dou y square is equal to 0. So this is coming in the energy equation. So this is coming in the Laplace equation. So when you have any source term, let's say this equation is revised in this way. So dou square u by dou x square plus dou square u by dou y square is equal to some constant or some source term minus dou p by let's say plus dou p by dou x. So you have this source term, this term basically, so we can take it as a Poisson equation. So instead of this, so you can take it as some constant c or some any term you take. So basically, so having a non-zero term on the right side will make this as a Poisson equation. Okay, so when you have it as 0, so we say it as a Laplace equation. So dou square t by dou x square plus dou square t by dou y square is equal to 0. So these two we can compare. Okay, you take either one or two. So what we do, so again we'll write this equation a into dou square phi by dou x square plus b into dou square phi divided by dou x dou y plus c into dou square phi by dou y square is equal to 0. Okay, so here if you compare, what is a is equal to 1, b is equal to 0, c is equal to 1. You take any equation. So here you have a is equal to 1, b is equal to 0, c is equal to 1. So again you take here, again you have a is equal to 1, b is equal to 0, c is equal to 1. Now what is happening actually? So when we do this, d is equal to b square minus 4ac. What is b? b is 0. 4. What is a? 1. What is c? 1. So therefore d is equal to minus 4. So d has become less than 0. So when d is less than 0, we say this as elliptic. Therefore, so what we can conclude? So the Laplace equation, or you take Poisson equation also, so it is coming under elliptic nature. So therefore, in this the elliptic case, so we have discussed that so the roots are imaginary. Okay, so when the roots are imaginary, so we have the propagation of the information throughout the domain with a complex nature, and one thing, so the speed of sound is very higher, and whatever the domain you take, so when you introduce any disturbance here at this point, at all points it is getting affected actually. So the range of influence will be everywhere. Okay, so the domain and the dependence, so the dependence of the domain will be everywhere, and the range of influence will be everywhere actually for the elliptic equations. Okay, so this is what we have for the elliptic equation. So which is coming under, sorry, which is the Laplace equation, which is coming under elliptic equations. Okay, and now we have the hyperbolic. For the hyperbolic, so we in the question we have seen the second order wave equation. So let us take dou square u by dou t square minus c square dou square u by dou x square is equal to 0. Let us take this. Okay. So again let us write this equation. So a into dou square phi by dou x square plus b into dou square phi by dou x dou y plus c into dou square phi by dou y square is equal to 0. Compare these two. What happens? A is equal to, what happens? So you can take A is equal to 1. So here you can see A1. So B is 0. C is equal to minus C square. Okay. So this thing let us apply here. So D, which is B square minus 4AC. Fine. So where B is 0 square minus 4 into 1, C is nothing but minus C square. So which has come as plus 4C square. Okay. So D has become greater than 0. So this is the case of hyperbolic equation. So in the tutorial question, we have seen the classification of elliptic and we have seen the classification of parabolic. So for classification of PDE for elliptic, for parabolic and for hyperbolic. So and there here like we have discussed what is unstudied heat conduction equation and what is Poisson equation. Sorry, what is Laplace equation and what is second order wave equation. So from the question, so what we have seen, so the first one, unsteady thermal conduction is parabolic. Okay. So next, Laplace equation is coming under elliptic. Third one, next, so we have second order wave equation, which is coming under hyperbolic. Okay, so we have these three. So we have proved it actually. So with this, we have seen. So let us actually see what is hyperbolic. So in the hyperbolic case, so we have d square as let's say 4c. So when d will be plus or minus 2 of root c. So here, based on this, what we have, so the roots dy by dx of 1 comma 2, so which will be plus or minus under root of 2c divided by 2 will be equal to plus or minus root c. So we have two which are characteristics equations. So those two, let's say we have one this way and other one this way. So if you take x and y axis, so we have one positive slope, or x comma t you take. So we have one positive slope, one negative slope. So whatever the zone of disturbance is there will happen in between these two characteristic equations. So whatever the whatever the disturbance you introduce here, it will affect this zone, but it does not affect this upstream zone. Okay, so the range of influence will be limited. So within in the certain zone. So outside this zone, the range of influence is is not present actually. Okay, so with this we have seen the tutorial question of the module 2. So the classification of the elliptic, parabolic and hyperbolic equation for the Laplace equation, for the unsteady thermal conduction equation, and for the second order wave equation. Okay, so in the next session, so we will see what is the tutorial question for the module 3, 4, 5, and we will see what is there for the grid, what is there for the finite volume method, and we will see some tutorial questions on those topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.